Our next speaker is Zach Tatlock from University of Washington. So Zach did his PhD from University of San Diego under Soren Lerner, and then he went to University of Washington as a faculty. Now he's associate professor at University of Washington. Soren did his PhD from University of Washington and went to San Diego, I guess the advisor and student treaty places. And so Zach, after he went to UW, has started to do a lot of things. And in particular, I'm very, fascinated by two pieces of work that he has done. One is on how to automatically tune floating point code, very hard problem. The second is the work that he's going to present us today. So for these actually two lines of work, he has won a bunch of paper awards. Distinguished paper was at POPL, PLDI, Uppsala, and so on, right? And also one thing I'm really, really impressed about Zach's work is he put out his tools. So both the work on floating point tuning and the egg libraries, all on GitHub with hundreds of stars and people are using. So I think that's impressive. Our community should do more of that. Yeah. Without further ado, let's hear from Zach.
Thank you so much. That introduction is far too kind. But everything that's good that's happened in the research I've been involved with is because of folks up here and more. This is sort of the crew that's been part of the core egg team, especially highlighting Max Wilsey, who's sort of Dr. Egg, and Chandra Kananandi, whose work sort of initially kicked off the egg craze. But it keeps growing, and it's been a lot of fun. So to sort of warm up, something that we do all the time in compilers, solvers, optimizers, on and on and on, is we want to transform some term from one shape to another. And the tool we almost always reach for is some kind of rewriting. So whenever you're doing term rewriting, you need rules. And it turns out that not all rules are created equal. Sometimes you have a set of rules that are really useful for a particular problem, and other times you have rules that maybe aren't so useful. So in this example, if we follow this sort of happy path of rules on the left, and we're going to apply them one after the other. I'm going to sort of pattern match here. I'm going to match that div. X will map to A, Y to 2, and Z to 2. I rewrite it. I get this nice form in the middle. Now if I apply that x over x goes to 1 rewrite, I get A times 1. And if I apply the third rewrite, I get A. That's great, right? Everything worked out beautifully. On the other hand, there are some pitfalls if I don't choose the right rules. So suppose that I apply this rule here at the top first, right? Well, maybe that's good. Maybe on whatever architecture I'm on, a left shift is cheaper than a multiply. But now I'm kind of stuck, right? None of my other rules apply. So I've gone off the rails, and it's very hard to do anything about it because I've lost information, right? I don't remember where I came from. On the other hand, maybe let's start over again and try the second rule, where I can commute the multiplication, but one challenge there is that I can commute it again. I can keep going on and on and on, right? So there's no guarantee this process necessarily terminates if I'm not careful. And also, how big can these terms get if I just keep applying the rules over and over and over? Well, this times one rule keeps enabling itself, right? So there are some challenges here. Now, on the other hand, while we've seen, these rules sort of going off the rails in these examples, for other inputs, for other workloads, these rules are going to be essential to getting the best results. So this leads to a question, which rewrite should I apply when? Now, there are classic results in term rewriting systems. People might be familiar with Knuth-Bendick's completion. That can answer this question, but those techniques are pretty hard to use. In fact, building a high-performance, reliable term rewriting system still remains difficult in 2022. So there's this other technique that we're really excited about called equality saturation. And the way it answers the question is by saying, well, just apply all the rules all the time in every order. I heard some sighs, which is right. This sort of very obviously blows up, right? So there's got to be some trick. Well, there's a few tricks that we're going to talk about. And of course, there's some asterisks in here. There's no silver bullet. But this approach, this sort of mindset, tends to work surprisingly well across a broad range of problems. So the goal today is to give folks a feel for equality saturation how the main tricks inside of it work, and then highlight some things we've been building to make this technique more practical for a broader range of problems. So for equality saturation, the real star of the show is a data structure called an E-graph. And this came from classic work on congruence closure algorithms. It's a data structure that sort of drives the heart of SMT solvers. And what we're going to do is rip it out of the SMT solver and try to do some new and interesting stuff with it. And one benefit is that, before this work, there weren't really just general purpose eGraph libraries. This was a data structure that was sort of hidden inside of SMT solvers, but it's a real gem. And so I think one of the benefits of equality saturation egg is sort of getting that data structure out there for people to do more interesting things with. Okay, so what the heck is an eGraph? So here's an eGraph on the left. And this eGraph represents that term that we've been trying to rewrite this whole time, right? Oh, sorry, I should explain what the boxes and things are. So the boxes are E-classes. Each E-class contains E-nodes. What's important about E-nodes, though, these operators, they don't point to other E-nodes. They point to E-classes, right? So there's this kind of layer of indirection. An operator points to a class, not to another operator. So it's not an AST. Right? So the E-nodes point to E-classes. Okay. And we also maximize sharing. So sort of a hash cons inside a memo table inside when I'm building this stuff. So I make sure I never duplicate anything, right? I have maximal sharing inside of the eGraph. Okay, so this particular eGraph right now, that root E-class up there at the top represents the term we've been looking at, right? A times 2 over 2. You sort of see, right, the divs at the root, the left-hand side's got the multiply with the A and the 2. You have the 2 on the right, but it's shared. So we want to be able to apply transformations, apply these rewrites. Remember, our whole goal was to avoid worrying about which rewrite to apply when. And essentially, it works basically the same way. So here we have our x times 2 goes to x left shift 1 rewrite. The difference, though, is that when we rewrite on an eGraph, we're not going to throw anything away. Right? So this eGraph, after applying this rewrite, what we did is we found that multiplication node, and we added the left shift in. So now that middle E-class represents both A times 2 and A left shift 1. So that one E-class represents both these programs. And as a consequence, the root E-class represents A times 2 over 2 and A left shift 1 over 2. And so this is one of the key benefits of this approach, is that we can't make a mistake, right? This is going to help us avoid that problem of taking a wrong turn, right? Of not applying rules in the right order. Because, if we apply a rule and it wasn't a good idea, we haven't lost anything. We didn't forget where we came from. We can always recover, any result we could have gotten before. So if we keep sort of turning the crank, we can keep applying our rules. And, things get a little bit hairy. But this is actually kind of neat because this eGraph, at this point, we're going to talk about a little bit more, not too much. You don't have to understand all the arrows and boxes and, oh my goodness. But this is at fixed point. If we apply our rules one more iteration, this won't change anymore, which is neat. That's where the name saturation comes from, right? What it means is that this eGraph has discovered all the equivalencies that are derivable from that set of rewrite rules we've been applying. A couple of other sort of interesting things that can be counterintuitive about using this term rewriting technique is that, the intuition is normally that the more rules I apply, the more things will blow up. And that can certainly happen for certain kinds of rules. But surprisingly, a lot of times in equality saturation, if your eGraph's getting really big, it's not because you're applying too many rules, it's because you're not applying enough rules. So if you notice in this last step we took, we went from what, 6, well, I think I put 7. Maybe I miscounted. Anyways, we went down in the number of E-classes, right? We have fewer E-classes on the right. The eGraph got smaller by applying more rules because more things merged, right? So actually, having more rules, learning more equivalencies tends to only make things better. Another thing that's kind of neat, if you look at this multiplication E-node up here in this top E-class, it's got a self-edge back. So multiplying by an E-class that has 1. So we've actually represented an infinite set of terms with this eGraph, and we can still rewrite over it just like normal, right? We sort of closed over multiplication by 1, by yourself by 1, by yourself by 1, on and on and on. And as we mentioned earlier, this eGraph is now saturated, right? So those are eGraphs. That's how we can apply rewrites to them. The idea of equality saturation is to sort of take that data structure and that term rewriting technique and use it as an optimization pass within, some kind of simplifier or an optimizer within a compiler, etc. And there's been some nice work in this space, especially by Nelson, who was the original inventor of eGraphs, and my colleagues and I in grad school, led by Ross Tate, extending this to work on loops as well. But the big idea with equality saturation, you got some term you care about. You want to make it better. So you put it in an eGraph, you apply rewrite rules over and over and over, and that eGraph grows. And then once you're satisfied, or the eGraph saturates, right, there's nothing left to learn, what you can do is extract out of that eGraph the best term according to some cost function, right? So this allows me to delay committing to any particular optimization, any particular choice of rewrite ordering, until I can see what its consequences are, right? So this is the key thing. I can grow the space of things I'm interested in, and then when I'm happy that that space is big enough, or I'm happy with the answers I've seen in there so far, I can pluck out the one I want. And that separation gives you a lot of flexibility. Okay, so the key, the real challenge here for extraction, there's different ways to do it. You can do sort of a bottom-up greedy traversal for things like size. It has a nice clean ILP encoding if you want to do common sub-expression elimination style extraction. But we're not going to talk about extraction too much today. We're really going to focus on this loop. So when you're applying rewrites, it breaks down into essentially 3 major steps. The first thing is I need to search through that whole eGraph to find the patterns, the left-hand sides of my rewrites. Then for every match I find for the left-hand side of a rewrite, I need to apply that, right? I need to introduce the right-hand side and merge that with the thing I found, right? Because the rule means that they're equal, that they're equivalent. Then there's this additional step, which is that the eGraph has, like any interesting data structure, several important invariants that it maintains. In the case of eGraphs, the big thing is that it maintains congruence, which is the guarantee that anywhere in the eGraph where I know that 2 terms A and B are equivalent, I also have to know that f of A and f of B are equivalent, right? So that's that congruence property. I have to push that up, and I need to maintain that in the data structure. But when I'm doing equality saturation, I often have a lot of rules, and I want to run them all over and over and over, so I get all sorts of orderings. I can see the effects of all sorts of orderings. So that makes this a really hot loop. So what we're going to focus on is how to make this fast, right? That's going to be the goal for like the next, 10 or 15 minutes or something. How can we make this loop go really fast? And we've been doing that sort of under the umbrella of this egg project. And so we'll talk about several different things, sort of brief highlights to provide intuition for how this machinery works. But let's go ahead and jump in to this performance thing. So if we look into how that loop is implemented sort of in Python, we're just going to step through this. I promise it's only like 8 lines of code. When I implement equality saturation, I take a term, chunk it into an eGraph. Then, while the eGraph isn't saturated, or I haven't hit some resource bound, what I'm going to do is I'm going to take each rewrite. I'm going to search the eGraph for matches to that rewrite. That's going to give me a set of substitutions in the E-class that the pattern matched at. Then for each of those, I'm going to instantiate the right-hand side with that substitution to get a fresh E-class. And then I'm going to ask the eGraph to merge those 2 E-classes. And I'll do that until saturation or timeout, and then I return the extracted thing. So what I want to highlight in this loop are how things are sort of phased, right? So when I'm actually executing this, I'm going to do a bunch of reads, right? So I'm going to do a search for one rewrite. Then I'm going to do a write to instantiate it, right? And also I'm going to restore the invariants of the data structure after every time I make any change. So I'm going to keep those invariants up to date. Every rewrite's only going to see a sort of well-formed eGraph all the time. This has some downsides though, right? Because I have this fine-grained interleaving of reads and writes, and I'm updating my invariants all the time in the data structure, and that's expensive. So one of the key insights of egg is, what if we just don't do that, right? What if we just don't maintain the invariants? So we're not going to go through this line by line, but this is at a high level how egg's equality saturation loop works. And the key features are that it batches all the reads. So I'm going to search all the rewrites and get all the substitutions before I apply any of them. So I have this big sort of read-only phase of the workload. Then once I have all the substitutions for this iteration, I'm going to apply them all together. right? So I get a big right phase. And then the key is that I'm going to restore the invariance once per iteration. And what's key about this design is that when I'm maintaining these invariants, the cost of restoring them is now amortized for all of the rewrites that happen in this iteration. I'm not paying for it per rewrite. I'm paying for it per full run of all the rewrites. And that makes things a lot cheaper. So how much cheaper? Well, if we look at sort of the traditional, I don't know if folks can see here. Oh, yes, question.
Yeah, I'd like to ask you about what invariants you're referring to, or if you're referring to the something about the congruence. Or what are these invariants, and isn't congruence automatically enforced when you anyway do something?
Yeah, so the most expensive, like the main invariant is congruence. There's also like hash cons, there's some other invariants, but the main one is congruence. And you have to restore it. And the thing that's frustrating about congruence is that you have to do it to fixed point. Because I guess I don't have the congruence property up, but if A becoming equal to B then causes me to merge f of A and f of B, well, that might cause me to merge g of f of A and g of f of B, and that might cause me to merge h of. So you have to walk arbitrarily up. Yeah.
But isn't this enforced because your structure is anyway within f? You see the A there, so you anyway do the A to a B, and so.
But this is the other way, right? The e nodes point down to arguments. Now I need to point up, and it's not just for that e node. I need to know its parents, with the functions its parents contain. So exactly, right? So this is the thing, like the congruence goes the other way. So if you were doing something like injectivity, you're all set, right? Because you're going down. But congruence, you have to go up. And so you have to maintain additional pointers. So it gets tedious. And the thing that's nice about this, this is still going to go to fixed point, but I can do these big full E-graph just rebuilds, right? These sort of linear scans over it. And those are really fast because caches are good. Okay. So how much faster is it? A lot faster. So this is sort of the traditional approach to restoring the invariance every iteration on the x-axis versus on the y-axis, doing it once per iteration, this sort of rebuilding approach. So if they were equally fast, things should follow this line, but it looks almost horizontal. And if we make it log scale, it still looks pretty darn good. And what's interesting is that we're getting sort of more speed up as we go. So this is on a set of equality saturation benchmarks. But this also will hold on real applications, as we'll see soon. And there's an example here. I have some hidden slides if folks want to walk through to get a little bit more intuition for how the amortization, you can get these big savings by doing it once per iteration. But there's a bunch of examples where basically something that might require order in work after every rewrite instead, which makes it n squared over all the rewrites. Instead, we can do it once and it stays linear. Okay, so there's one other key performance trick that's been really important in egg I wanted to emphasize, which is this idea of batching. So traditional equality saturation sort of works this way where I take a term, put it in the E-graph, turn the crank. Now we have a better loop, which is great, and then I extract. One of the things that we found has been a huge enabler and given a lot of performance in several systems that we've built or helped other people build has been this idea of batching. So instead of working on one term at a time, for a lot of applications, you have a lot of related terms. So we just throw a bunch of them in the E-graph at once. And then at the end, we can extract a result for each thing that we'd added. And what's really nice about this is, once again, we're all of the shared structure between terms. If the terms are similar, optimizing one, all of the terms that have any shared substructure also get optimized for free at the same time. There's this additional effect, which is kind of neat, because if you think about the E-graph, you start with a term, and you apply rewrite. So you're growing out from that term, right, to sort of nearby within some number of rewrite applications, equivalent terms. But when you have multiple terms that can kind of have the search space, right? If these two terms are sort of both growing out, it's a lot easier for them to meet in the middle. So there's this neat effect where it's not just that it gets faster, you also can get better results. Right? It makes it easier to find equivalencies because you have sort of a shortcut with these other related terms. So anyways, just doing batching actually can lead to huge speed up. So one of my favorite examples actually, Zendong was talking about Herbie. So Herbie's a big user of E-graphs, and we actually had been using equality saturation in Herbie for a long time before egg. What Herbie tries to do is take, here's like the quadratic equation, take some formula, which I don't know if folks know this, but it turns out like the naive implementation of quadratic does not do so well on floating point. So here's the error, or the log of the error, the bits correct roughly, versus B for quadratic, randomly sampled over a bunch of inputs. And what Herbie will try to do is rewrite the Wikipedia version of some formula into some monstrosity that's very hard to read, but performs much better when you look at the error, right? So you don't have to read it, you don't have to write that code. The idea is that the tool's doing it for you. But a huge part of Herbie's workload is actually doing simplification on these terms, and it's churning through tens of thousands of candidates, and so that adds up. So when we did batching in Herbie, even without rebuilding, even without amortizing invariant maintenance, we got a huge speed up, almost a 40% speed up on Herbie just from batching, right? Just by throwing a bunch of expressions in the eGraph all together. It also improved the quality of the results. And rebuilding on top of that pulled in some more speed, but then going to egg basically made simplification free in the context of Herbie. So, okay. Oh, yes.
Excuse me, I didn't understand the meaning of throwing a bunch of terms into your classes, because before, if you start with one, you are computing the equivalence class of this term, right? If you go to saturation. But now, how do you keep track of the individual?
That's a great question, yeah. Yeah, so basically, let's get to a slide that has an eGraph. Yeah, so basically, whenever I add a term, so whenever, in the egg API, or a lot of eGraph APIs, when I add a term, what I'll get back is an eClass ID, which is actually like a union find ID under the hood. So when I add a term, I'm just going to remember the eClass I got added to. And then after I've saturated or run, I can extract from the eClasses for everything I added. Right? So suppose, sake of argument, suppose I added a times 2. I got back eClass 1. And then I also added, a times 2 over 2, and I got back eClass 2. Then I'm going to turn the crank, and at the end, one of these eClasses, let's see, I guess it'll be this one, will still be 1, and I extract from, wait, it was times 2? Yeah, this one will still be 1. So if I extract from it, I'll probably get, I don't know, a left shift 1 or something. And this will be eClass 2, and if I extract from it, I'm going to get a. So I can just, for each eClass, for each thing I added, I can extract from its eClass whatever the cheapest version of that term is. Yeah. I know what class they ended. I know what class they started in, and even though they merge, under the hood is a union find, right? So maybe now in this world, like at this point, the eGraph, maybe this eClass is actually ID 17. I don't know, but when I do find in the union find to get the leader of 1, whatever it initially was, I'll get the right leader number. So it's just classic targen union find under the hood. So when I ask for that old pointer and follow and do the find on it to get its leader, I'll get the right eClass. It'll still be in there. Okay, so batching is great. And between deferred invariant maintenance and batching, you get substantial speed ups compared to past approaches. However, we then had the problem that you often have, which is that when you fix one bottleneck, something else is slow, right? And so, what happened was, now in this loop, this sort of the hot loop inside of EXAT, invariant maintenance was no longer expensive. What was expensive was we have to search the whole eGraph. And as you apply more rules, the eGraph gets bigger and bigger. So what are you going to do? So in general, this is a problem known as e-matching. Basically, it just means you got a rewrite rule. You have some pattern. You want to search the whole eGraph to find matches for that. So, here's another example eGraph drawn in a slightly different style. We've got n plus 2 e-classes. This one here at the top, all of the operators in it are called F. This one in the middle, all the operators are called G. And all the terms are, F of some constant applied to G of that constant, right? So, when I'm doing e-matching, what I'm doing is I'm taking a pattern and trying to find substitutions such that if I apply the substitution back to the pattern, I get a term that's represented in the eGraph, right? So if I wanted, for example, f of some variable, like f applied to some variable and g applied to that same thing, right? So f with some e-class and g of that same e-class, I can get n matches because I can find f of 1, g of 1, f of 2, g of 2, dot, 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 f of n, g of n, right? So I can get n matches here. In contrast, if I had I was just looking for f1a, well, I only need one substitution, right? Because there's only one way to have f of 1 in this e-class, and it doesn't matter what I pick for the right-hand side. It's just a variable. It's just free, basically, right? So one thing to notice here is that there's a couple kinds of constraints. This is going to be really important for us. Some of these constraints are structural, right? So when I'm looking at this pattern, I know, oh, well, I want to find a g as the second argument to f, right? That's just part of the sort of tree shape of the pattern that's well represented. So that sort of structural constraint it's not, traditional recursive descent will, backtracking will be okay. But there's this other kind of constraint in the pattern, right? This variable, this equality constraint, alpha, forces me to match the same thing here and here. And the structure doesn't capture that equality constraint, and that can sort of occur arbitrarily. So this can be really hard because I have both structural and equality constraints, whereas this pattern is easy because alpha occurs once, right? It's linear. It's just a freebie. It's a wild card, right? There's nothing. I don't need to be smart. That's only structural. It turns out this problem's NP complete, but I think that's kind of misleading, although it has stopped people from necessarily digging too much into it. It's weird to prove NP completeness with respect to pattern size, at least for equality saturation, because the patterns you're searching are small, right? Usually like 5 to a dozen nodes or something, so it's not that big a deal. So one key insight of this work was we should really not be thinking about this, the complexity in terms of the size of the patterns. I should be thinking about it in terms of the size of the E-graph, right? I ideally want to think about it in terms of the number of matches that are there to be found, right? And that's how I should think about efficiency. Okay, so how do people, and egg included, how do people used to do E-matching? Well, basically, if you had some pattern, you walked the tree, and as you recurse and find substitutions, and as you came back up, you check the substitutions from the children, sort of do a cross product, a join almost, to make sure they were consistent. Yes, Saman?
Something like that, can't you go bottom up because alpha merges at the end?
Yeah, so you can do it bottom up, or you can do it top down. I'm going to show top down. And I'll talk a little bit. So Leo also had, people for SMT solvers have done a bunch of optimizations on E-matching, but they all sort of boil down to some kind of backtracking-based search. Right? I can make a queue instead and go bottom up, and I can also do a lot of caching, like with mod time analysis. Leo has this whole thing with like a very fancy and cool virtual machine. So he compiles them down so you get sharing among sub-patterns. So people have been very clever here. But, okay, so basically this is going to work the way folks think it is, at least the way I think you think it will work. I'm going to go through every E-class in the E-graph. If I find an F, right, that's what this, will this work? Oh, it does a thing, maybe. Oh. Okay, so I'm going to start at the root. I'm going to look for E-classes that have an F. I don't care what the left-hand child is. I'll match anything. And then within whatever E-class is to the right of that F, I'm going to go through all of its children, right? And I'm going to get a substitution, but I need to make sure that it matches. So if you sort of think about this trace of all the things being compared, right, there's sort of n-squared things in this E-graph that I'm going to consider, but only n of them will be valid matches. Because I don't figure out this equality constraint until after I've come back from recursing. Right? So I'm going to do like quadratic work instead of linear, and that's a bummer. And this is true basically of all existing E-matching techniques, right? So people have done a lot of really cool, clever stuff, but they don't have bounds. They show that it works well in practice, but it's very hard to analyze, how these things work in general. So our big idea was, it turns out that everything was done in databases. You just have to find the magic keyword in the right mapping. And if you think about E-matching as this problem of answering conjunctive queries, then all of a sudden you're blessed with a bunch of very nice bounds that you can apply. So what we want to do is we want to figure out how can we turn this graph search into a database query. And if we do that for the very first time, we can get tight bounds on the optimal E-matching, right? So I feel like it's a big setup. It's going to be disappointingly simple, but I actually find that really a charming aspect of this work. Okay, so I got some eGraph. I got some patterns the user wants me to search for. Here's what I'm going to do. I'm going to translate the eGraph into a set of tables. We'll see exactly how that works, but basically, instead of having this E class with a bunch of different operators, I'm going to kind of turn it inside out. I'm going to make a table per operator. We'll see an example in a second, but turn the eGraph into tables. Then I'm going to compile the queries into conjunctive queries. This is basically just a linear pass over the queries. Then I'm going to put those into a query execution engine, right, with join planning and profit. That's really it. So why does that, what's the trick here? Well, the trick is that when I make my E-matching patterns, my rewrite patterns into conjunctive queries, it means I don't have to execute that query top down or bottom up. I don't have to do structural first or equality first. I can do them in whatever order I want. And I can take advantage of all kinds of things, the stuff that database query execution engines take advantage of. I know things about the sizes of the tables, right? So I can plan in an optimal way how to execute that query. I can execute the query middle out, right? I can satisfy the constraints in whatever order will be optimal. And so this flexibility is really the key. I no longer am forced to go in any particular order when I'm matching, right? And that's the magic. Yes?
So you can also use data logging, right?
That's exactly what it is, yeah. Exactly, you're right, yeah. The conjunctive queries, it's exactly data log. Exactly. And yes. I'm very excited about data log and equality saturation. It turns out that there's a bunch of cool stuff there that I would love to chat about more this afternoon. I don't think we're gonna have too much time in the slides, but it's the future. Okay, so we had what, 2 steps, right? I gotta turn the eGraph into a bunch of tables, and I gotta turn the queries, the patterns into conjunctive queries. So turning the eGraph into tables is really not that bad at all. Like I said, we're just gonna make a table for every operator, right? For every function symbol. We're gonna make another table. And each table is gonna have a column for the E-class ID, right? And then a column, it'll have a column for each argument. So F is a binary operator. It's got 3 columns total, 2 for the arguments, the left and right hand side of F, and 1 for what E-class it's in. And so what happens now is that every E node in my eGraph will be 1 row in this table, right? So this first F here on the top left gets represented as this row, right? It's in E-class CF, the class for F that we made. Its left argument is in E-class 1. Its right argument is in E-class CG, right? So you're just encoding a table. This is another view of the graph, right? You just kind of transpose it in your mind with respect to the functions. Not too bad. Is everybody okay with that? Seems, okay, great. So now what do I do with the queries? So I need to turn these into conjunctive queries. And this is also just not that bad, right? So essentially, I'm going to have a set of relational constraints with these variables. And that's it, right? It's literally just a pass. I just have these equality constraints between the parts. And I've phrased it in terms of the tables I built. And then I just need to execute it. So in this case, for example, maybe I want to make an index over the table I built for that G operator. And now I can just go bop each tuple on the head, checking if it's an index, and if it is, I add it. And what's really nice about this is that there are no X's, right? Because I know what the query looks like, I can build indices. And I don't waste any time checking tuples that can't possibly match, right? I'm just going to compute the output, literally, right? So there's more to this, and it's in the paper. There's an algorithm called worst case optimal join, which was developed surprisingly recently in the database community, sometime in the last 10 years, maybe 9 years or so. And with that, we can get these really nice tight bounds. And I don't think well, we'll see. I have a slide on it, but I think it's hidden right now. So like I said, right, the key insight is that by turning this into a set of conjunctive queries, now I can execute that against the database tables in whatever order I want. And that gives the query planner the freedom it needs to do things optimally. Traditional approach can only do structural, which our new approach can do. But the nice thing is it can also take advantage of these equality constraints without waiting for the recursion to come back up and then check the consistency with other backtracking searches. Okay. So it works because it's asymptotically faster. So we get, let's see, 6 orders of magnitude speed up on that benchmark. Sometimes, building the index takes time. You might be wondering, like, well, gosh, why do you keep building the index every iteration? That seems really wasteful, doesn't it? What if you just had like a data log engine that knew how to do congruence, right? And I would say that's a really good idea. Hopefully when you review our paper, you will think so too. So the other thing is that, sometimes we don't get much speed up. In the cases that you have these sort of linear patterns where equality constraints, you don't reuse the same pattern variable in multiple places, you can't beat the backtracking search because there are only structural constraints. So the backtracking search isn't really wasting any time, right? That only sort of arises when you have these equality constraints. One last thing that's really cool about e-matching this way is that you actually get more expressiveness. So a common pattern that, especially when people were working on ML kernel optimization frameworks with egg, that people often wanted was this ability to search for multiple things in the e-graph. So all the rewrite rules we've written so far, they have a left-hand side and right-hand side. And what do they mean? They mean find the left-hand side in the e-graph, apply substitution to the right-hand side, put that in the e-graph, merge the left and right? Each rewrite means sort of introduce one more equality, right? Find one more equivalence, one more fact. Here we're doing something a little bit different. Here what we're doing is we're saying, hey, search the e-graph for these 2 different e-classes that we are not going to make equal to each other. I just want to know, are there 2 e-classes? Actually, they don't have to be different either. Are there 2 e-classes that match these patterns? Right? So are there 2 map moles where both have A on the left-hand side? And if you find that, I'd like you to merge the first thing to be equivalent to whatever I get by doing the map mole on the concatenation of B and C, and then splitting out the result for B. And the second thing to be equivalent to whatever I get by doing the map mole of A on the concatenation of B and C, and splitting out the result for AC. And so this is nice because now I've made a bigger, denser operation. So I think there's some way to probably tacoify some of this sort of stuff, right? But basically I'm doing this reordering where I've sort of fused, and I can split out and reuse a single map mol call, right? Because this one map mol will be shared. I can pull both results out of it rather than doing 2 calls to map mol, right? And this is nice because in relational e-matching, this is just a database query. If you're taking the traditional sort of backtracking-based e-graph approach, it's not entirely clear how you do it efficiently. I mean, I guess I have to do 2 full e-matches and 2 full, searches over the whole e-graph, recursing down to find stuff. Okay, so that is sort of everything on that's basically everything on the performance side. I wanted to really quickly mention something that's nice in egg has proven really powerful, although I think that it will hopefully change a lot soon, and for the better, but the idea is still good, is the idea of e-class analysis. So far we've only been talking about rewrites, right? Syntactic rewrites. It says, hey, find some part of the e-graph that looks like this, transform it to something that looks like that. But I'm literally writing out syntactically the left and right-hand sides of each rewrite rule. Well, how many rewrite rules will I have to write down to do constant folding? All of them, right? Like it's not a syntactic thing, right? I need some way to bring the semantics of the language in. And there's a bunch of other stuff where I care about like understanding the meaning of terms more, maybe some kind of conditional rules. And in general, many optimizations require some analysis to enable them, their sound application. So in egg, we have this idea of e-class analyses. And basically all I do is I'm going to tag every e-class with some additional information. And in the case of constant folding, right, what that means is I'm going to say like, okay, well, whenever I make a new leaf e-class, it'll get tagged with one of these analysis facts. 2 is a constant, so I'm going to tag that, oh, this e-class has the constant 2. A, I don't know anything about, so it doesn't get tagged with anything. And that information sort of percolates up. So this multiply is going to say, okay, well, if you multiply I don't know by 2, well, you're still just going to get I don't know, right? And same thing if you divide I don't know by 2, you still get I don't know. But let's say for whatever reason in our workload, we learned that A and 2 were equivalent, right? We had merged these. Now when we percolate this up, right? Well, 2 times 2 I know is 4, and 4 over 2 I know is 2, right? So that kind of information can sort of flow throughout the E-graph. Much like, you're moving analysis facts around. If this feels a little bit abstract interpretation-y, you are absolutely on the right track. So essentially, the domain of facts, we assume forms some lattice, and there's a way, whenever a new E node is made, it has some initial fact drawn from that domain. Whenever two E classes get merged, you apply the merge function for the lattice. And there's optionally also a modify function, which is useful for some kinds of analyses like debugging. You can sort of have watch expressions, things like this. Sort of just going to call back whenever anything happens to an E class. But the key thing here that I think that I'm really excited about is I think that this is a potentially really interesting way to make static analysis more robust in general. Right? So static analysis is often quite sensitive to the syntax of the program you're analyzing, because you have a bunch of syntax-driven rules, right? You say, like, oh, well, if I know this fact, and I come across a program that has this shape, then here's the next fact I know. But that means that you're very sensitive to how the programmer wrote the program. So here's an example from our friend Sam Coward at a workshop, eGraphs workshop this year. And he's very interested in numerics and floating point analysis. And one of the things he was pointing out is that if you assume, x is in the range 0, 1, y in the range 1, 2, these three equivalent programs all have quite different intervals, right, with a very simple sort of interval arithmetic. But if you put them as analysis facts in an E-graph, well, my merge function can always take the max of the mins and the mins of the maxes, right? Because each of these are sound bounds, then they're equivalent. They denote the same value. They're equivalent expressions. So this is a way to get precision by equivalence, right? The same rules that I'm using for interval analysis sort of combine with my rewriting to give me a much tighter overall bound, right, -1 to 0, than I would get with any of the individual versions. Right? So I sort of get the best of all worlds. I'm sort of doing program analysis modulo equivalence. I get the bounds from the tightest version that I can find. And so if there's some nice things in this paper, but there's this sort of example. It's a short paper too. It's very nice. But you can sort of see how, as you apply rewrites, your bounds get tighter for the expressions in the E-graph, right? And they only get tighter. So that's something that's pretty exciting. Okay, so unfortunately, I have to switch decks because it turns out that after a certain number of slides, Google Slides will really freak out, as you can see by the beach ball spinning. So I just wanted to talk about a couple more things. So that was sort of, that's sort of the core egg machinery that I wanted folks to see. In particular with these E-class analyses, one of the things I'm extremely excited about is back to this data log idea. Analyses, right now you write a sort of Rust code on the side. You write all of your rules, which the EXET engine applies, and then you also write your analyses and the code to define the facts and propagate them. You write in some sort of Rust code on the side in egg. But I think if you really take this data log idea, data log plus congruence idea, to the extreme, you can do everything in terms of rules. And I think it'll be very clean and very nice and very compositional. So I am super, super jazzed about that. But, stay tuned. And of course, very happy to talk about it after the talk, or chat about it after the talk, I guess. Okay. So with EXET, you got this problem. Does everybody get it? Okay. Yeah. So EXET can only be as good as the rules that you're running, right? But where do the rules come from? If you don't have good rules, then EXET's not going to work for you. So you're not very motivated to write good rules. Also, writing rules can be really expensive and difficult. So we were thinking about this. For a long time, there wasn't a nice, extensible general equality saturation engine like egg. So a lot of problems that we wanted to go play around with didn't have rule sets. And that can be, it can be really tough to get started, right? Like we said earlier, sometimes when you're getting bad performance, often when you're getting bad performance with EXET or egg, is because you're missing rules. You just haven't thought of enough rules. So we thought how we might be able to, we thought about sort of how could we apply egg to give a spin on this very classic approach to inferring equivalencies, to inferring rate rules. So there's a bunch of papers that all use roughly this recipe, right? Step one is I got some grammar. I'm going to enumerate a bunch of terms. Actually, Hila had this earlier today, so you've already seen it once today. So I'm going to enumerate a bunch of terms from some grammar. Step 2 is I'm going to evaluate them on some concrete values and get what we're calling fingerprints here. Sometimes they're also called characteristic vectors or CVECs, whatever. And then I'm going to use the sets of these terms that come out equal to suggest likely equivalencies, right? So maybe it turns out that x plus y and y plus x, when I evaluate them on concrete values, they keep coming out the same. I think, hey, that might be a good rule, right? I can find other rules like x plus 0 goes to x. But I also might find some rules that aren't so hot, right? Like these two will also, x plus y and x plus y plus x. That'll also always evaluate to the same thing. But that's not a very good rule, right? It's not minimal. It's not orthogonal with respect to the other rules. So then this last step is I want to somehow figure out which of these rules are worth keeping around, right? How do I get a good set of rules? So what we wanted to do is figure out, well, can egg help with, this recipe? And what we found is that actually we can use ECSAT to make each of these steps better. So we built this system called Ruler that automatically infers rewrite rules, given a grammar, an interpreter for that grammar, and then some kind of rule validation. And we'll talk about why we feel pretty good being flexible with the way the validation is done. So let's go through each of those steps and see how Ruler uses ECSAT and egg to make that faster. So normally when you're enumerating straight from the grammar, right, you can never get too deep because there's exponentially many terms, right? Things blow up. And that's still going to be true even for ECSAT and egg, right? Like it's a real steep exponential. But one of the things that's nice is that we can enumerate over the E graph instead of on the raw terms. And this has a bunch of benefits because now, as I find equivalencies and merge things, there are exponentially fewer E classes, right? So it gives me sort of another 2 or 3 steps in the enumeration for free that I wouldn't get if I was just enumerating flat terms. And the other thing that's nice is as I'm enumerating, I'm learning rules, right? So I'm going to enumerate some, learn some rules, and then I can apply those rules to shrink the E graph, which means I'm shrinking my enumeration space, right? So there's this nice sort of feedback where as I'm enumerating, I'm learning rules, which shrink what I'm enumerating over, which lets me learn more rules. And this sort of virtuous cycle lets us get a little bit deeper in the search space. Okay. So this neat thing where we're applying the rules as we learn them, and that enables going deeper, finding more rules. For candidate generation, Ruler basically works at a high level pretty much the same way as traditional rule inference tools. I'm going to have a vector of inputs that I run for each E class. I'm going to evaluate it, and then when I find 2 E classes that have the same fingerprint, that'll be a likely rule. And we can then validate those however you want before we sort of add them. But this third step is where things get really interesting and nice in Ruler, which is that I can actually use ECSAT where my terms are actually themselves rules. So after I do that fingerprint matching, I'm going to get a bunch of candidate rules. As the search space goes deeper, I'm going to get tens of thousands of rules. And somehow I want to filter those down to sort of the small orthogonal core rule set, right? The rule set, we call them the whiteboard rules. It's like if you were teaching somebody about a domain, these are the rules you would write out for them. That's what we want. So we apply some heuristic and just pick a small number of top K rules. Basically, we order this by size and subsumption, right? So if a rule is more general, would unify with another rule. We pick those. So we pick a couple of those. And we add those to our database. Then we'll have a large number of remaining rules. So we just make an E graph out of the rules, right? For each rule, I'm going to add 2 things in my E graph. I'm going to add the left-hand side and right-hand side for each rule, right? So there we've got 4 rules. I've got 8 E nodes. They've got left and right of the first, left and right of the second, left and right of the third, left and right of the fourth. Now what I'm going to do is I'm going to run the rules I've learned so far, plus the rules I picked, and see which of these other rule candidates merge. And if the left and right E nodes for one of the candidates merge, that means that rule is derivable from the rules I've already learned. So I don't need it, right? I already have that much proving power. Adding that rule wouldn't give me anything. I can already derive that rule from the rules I have. So I'm going to kick them out, right? And then I can rinse and repeat. If there's rules left, then I'll again, look for the smallest, most general ones, take them out, put the rest in, run again. Hila. for a while, yeah, I mean, once you get to like depth 4 or 5, it's, yeah. I mean, it's a synthesis tool. There's a heuristic somewhere. But I mean, you'd be surprised how far you can actually get. You can get pretty deep for, well, what I'll show, we did this for rational, for Herbie rules. And you can get surprisingly deep on this stuff. Okay, and I think that we are burning daylight, but luckily we are close. So what's nice is that, again, right, we're using the rules as we learn them to keep learning better rules. So, how do we know these rules are right? Because we're just really starting with the grammar and an interpreter. I said some kind of validation technique. And the reason that I feel kind of okay hand-waving about that, of course, in general, right, if you don't prove a rule correct, you're going to be in trouble. But what's neat is that ECSAT is really good at letting you know when you have an unsound rule. And what tends to happen, so we have some examples of this in the paper, is when you have an unsound rule, and for example, you have some arithmetic domain, if you have a bogus rule, you will often very quickly end up merging distinct constants. And egg will crash, right? So ECSAT is very good at exploiting unsound rules, which real quickly cause a couple of constants to merge. So we did some analysis to see, well, how often is it the case that we found an unsound rule, and we sort of validated this with domains that we had an SMT verifier for. How often is it we found an unsound rule and SMT didn't crash? And it depends a little bit on the domain, but typically if you have an unsound rule, you'll crash after a couple of iterations. And so that gave us a lot of additional confidence, this sort of ECSAT soundiness, sort of a nice thing, an observation from this work. Okay, so Ruler is up. It's also still under active development, working on additional techniques to help guide the search, right? Have some sort of human-in-the-loop expertise so you can get deeper into the search space for finding rules. But yeah, super excited. It was a lot of fun. We compared to CVC4. We are about twice as fast. We find about an order of magnitude fewer rules, and we can derive more equivalences than them. It's actually hard to compare sort of proving power in this way, but this is a ratio by trying each set of rules, trying to derive all the rules in the other set. So Ruler's fast, gives you a much smaller rule set in about half the time, which is pretty cool. We also looked at Herbie, and we focused on the rational subset. Herbie normally works on reals. Can't have an interpreter for the reals. So we went through and learned some rewrites that closed some long-standing open GitHub issues. Again, it was really fast and basically as good as the human-written rules when we replaced the entire rule set, not just those missing ones we found. So the last thing I wanted to do is just highlight a couple of applications. This one is actually one Chandra did that started the whole egg thing. I just think it has a nice worldview for folks in the audience. Essentially, this is basically a compiler pipeline diagram. When you're making stuff, you're translating an idea into an output by a sequence of meaning-preserving transformations. That sounds like compilation to me. And when people are doing this with 3D printing, a lot of times it's hard to design stuff, so they go download things from the internet. But the problem is those come in formats that are easy to just throw on your printer and go. They're really hard to edit. So the idea was, could we decompile the designs people actually share back up to something that's much easier to modify? And so we built this tool called Solinsky that starts with, a big set of triangles and then uses a quality saturation to decompile it down to a small, simple program, which is very easy to edit. It lets you make variations of, whatever part you want to make. And this is actually where Egg got started, was supporting this workload. There's a very nice technique in this paper on inverse transformations that helps mitigate challenges from what's known as the AC matching in the congruence closure literature. Just a paper I really liked and was really successful. We also just got a POPL paper in doing library inference. Kevin, I think, has a similar thing going on in this space. We were using his benchmarks, which were very helpful. So using Egg and ECSAT. This is work led by Nadia Polikarpova at UC San Diego. And we also have been working a lot on trustworthiness. So, Egg is a large, complex, automated reasoning engine. Why should you believe the results you get out of Egg? And our friends at Intel asked us this same question because they were using Egg to optimize data paths, and they got some cool results, but nobody would let them ship it because you have to prove it correct. And so we added proof production, but then we found out that that's actually a pretty hard problem to get small proofs. So we have a paper at FMCAD. Oliver Flatt's going to be giving a talk in a couple weeks, where we find much smaller proofs out of eggs optimization passes, and that led to like a 2x speed up on verification at Intel. On a small set of benchmarks, we get about 30% smaller proofs versus Z3. So sorry, that was kind of whirlwind there at the end. I think I'm a little bit over. Apologies. Oh no, I still got 2 minutes. Great. But yeah, so this is sort of the EECSAT thing that's been going on. It's a project I really love. It's a lot of fun. It's the community is really nice, so would love for folks to join. There's a really active Zulip. If you just search like egg eGraphs, you'll find the eGraphs webpage. The Zulip's there. There's like a community wiki chat thing on the GitHub. Yeah, and there's a bunch more papers that we didn't have time to talk about that we're not writing at all, right? So like a lot of other people are building cool stuff. Fastly's using it as well. Sortora, Melissa Gives' startup is using it. It's just it's really fun right now because there's a lot of cool new stuff to figure out, especially Datalog. I don't know who said that, but Datalog is that's going to be a big thing. So thank you all very much.
Okay, thanks, Zach, for a very nice talk. I think there's a question, maybe I'll run to you.
I think you briefly mentioned it, like abstract interpretation. Like this data structure, can it be combined with abstract interpretation to like infer deeper, more precise rules? Not precise, like more, I don't know, advanced rules.
So when you say more advanced rules, you mean like more precise facts about a particular program, or? Yeah. So, the examples that we've been working with are things just like interval analysis for numerical stuff. So pretty simple things. Although, interval analysis can get quite subtle. I think my suspicion is that it's more going to work the other way. So right now, I feel like I'm not an abstract interpretation expert, so somebody holler when I, put my foot in my mouth. But my intuition is that really smart people think really hard and carefully design their domain and rules so they can get precise results on a broad range of programs. My intuition is that, kind of in the same way that with egg, you could design a fancy term writing system like Knuth Bendix et al. And think carefully about orders and termination, all of that. Or you could just use EECSAT. I think similarly for analyses, what it'll mean is I can write a very simple analysis, but it'll sort of cooperate with the rewrites. So it'll allow me to get analysis results which are as precise or perhaps better in some cases as I would have gotten if I carefully designed my abstract interpretation or my data flow analysis or whatever. So I can write a much simpler analysis, but I combine it with the rules and I still get very precise results. So my intuition is it's more about making it easier and more accessible than necessarily much more precise. But this is still very early, so it's a great question. And it would be very interesting to do some kind of systematic survey of this.
Yeah, really cool stuff and really cool talk as always. Very basic question. So most of the examples you've shown actually have to do with rewriting purely functional code and expressions. So what if I want to use egg for implementing something like a peephole optimization that relies on some preconditions like what Nuno was talking about earlier today? So would it be useful in any way?
Yeah, sure. I mean, so the paper where we coined the term EECSAT was for a Java compiler. So basically, you just put it in the state monad and go. And that limits sharing, right? So I can thread the state explicitly. And statements are now state transformers that all take this a state and produce a state.
Well, assuming you have no ls in or things. So you have all unique variables that might work. If you have ls variables, I'm not sure. But maybe this is something we can.
Yeah, we should sit down. I mean, you're the separation logic expert, so we should sit down and work it out. But we definitely had objects in Peggy and did a bunch of optimizations. So there's a lot you can do. That answer is it's true. Like we've built EECSAT tools for imperative programs this way, and it worked well. It's also sort of you're getting handcuffed, right? Because it limits the sharing you can have. Like you need to know what commutes. So this is like, for example, like knowing things don't alias would let me commute more assignments, right? So that would be the kind of thing I'm missing out on. If I don't have alias information, then I can't reorder those assignments because it might change the meaning. There's also I think there's this general question about context. And, what's his name? I feel so bad. He works with... Okay, I'm going to feel very bad and say that. Anyway, some people have been working on context, and that might help too. But it gets very tricky. So I would say basically you're right. If you can encode your problem in a way that it's pure, you're in business. If you can't, it's not game over, but it does get harder. And we haven't done as much of that. Yeah.
Okay, great. Let's thank Zach, and you can talk to him during the break.